Okay, we have the last part of the magnetic materials. It's a brief uh, lecture on the, so let me share my screen and so let me get to, okay, so this is lecture 7B2 and it will be on auxiliary field H. One more new character to be introduced to complete the all the variables that we need for Maxwell's equations. Okay, and of course Ampere's law for free current, analogous to what we had in electrostatics. So let's consider the what is called the auxiliary field H. Okay, so recall the Ampere's law. Okay, that was del cross B, or curl of B is mu naught J, and its integral form is B dot dl mu naught I enclosed. So the current density or the current that is included here, all that is both free and bound current. In the last lecture, I had discussed about bound currents. So when in these Ampere's law in differential form and in integral form includes both free and bound currents. Now, hence we rewrite it as, let's say, we can always write just 1 by mu naught del cross B J as free current plus bound current. Okay, so there is no new physics. It's just that I'm writing it for my convenience. So then, and I know what is JB, the bound current, volume current. This is curl of M. Okay, so del cross M and JF. And now what I do is I bring this del cross M on this side. So del cross B is there. All right. So B by mu naught minus M, and that is the free current. So now I have an expression which is on right side only free current, and on the left there is a new quantity, and this quantity I call as H. And we define, so after converting the bound current in terms of magnetization, we define H as this quantity, B by mu naught minus M. Okay, so the modified Ampere's law then reads, okay, simply that is del cross H JF. That's neat. So JF is the source, or the curl of H is simply JF, and that produces H. So now something, so now only in terms of free current. Okay, there might be bound current, but that is already included through the magnetization. So in integral form, this would also become H dot dl for the Amperian loop, okay, and that will be the total free current which is enclosed, okay, only the free current that is enclosed. So this will become the basis of calculating H first, okay, whenever we can, using the free current, and then maybe go to B. Let me make some comments about H. Many experimentalists often refer to H as the magnetic field because this is what we experimentalists work with in the laboratory, okay, or magnetic field intensity. These are the names that is given. Then B is then given a different name. Sometimes it's called magnetic flux density or is magnetic induction, etc. In laboratory setting or even engineering textbooks, these are the kind of terms that is used. But B is very fundamental, and hence we'll call B as the magnetic field and H is the H. That is what Griffith recommends, and I agree. So we will consider B as magnetic field and H as the auxiliary field, as I have mentioned. All right. Okay, so now let's go to what is the importance of H. Okay, let's consider that. So it is clearly analogous to D in electrostatics. We remember in electrostatics, we had divergence of D as free charge. So the bound charge was taken care of, okay, in terms of polarization, and we had D defined as epsilon naught E plus P. That was the definition of the displacement vector D. So this is similar. So del cross H, JF, and of course H is B by mu naught M. Okay, so there is a corresponding relations. As I said, we have to always keeping track of what was that in electrostatics and how is it is in magnetostatics. Okay, so that was for the Gauss's law, and here is for Ampere's law. So experimentally, we control free current in the lab, and hence H is commonly used as the primary or independent variable, and B is the dependent variable. Free current is easily measured in the lab using a meter, ammeter. In contrast, we normally control E in the lab by applying voltage, okay, from a battery or cell or somewhere, which is also easily measured using a voltmeter. So in the lab, what we manipulate, okay, depends on equipment and facility. So this free current is something that you can manipulate from outside. And the voltage you can manipulate and measure an ammeter. So we don't have a D meter, but we have a voltmeter. Okay, and hence H and E are used in the lab more frequently, though theoretically H and D are in the same footing. Okay, and E and B are on the same footing in terms of the framework of the theory. So let's see, what do I mean by control? This is I hope you have seen electromagnets like that. There is an iron core and there is a winding. Okay, so what do we control? What we control is the current that we put into this goes and to the winding, so that we get a magnetic field between the two pole pieces. Okay, and so we control the free current into this, and then it is, of course, uh, goes around the iron core, and there is a pole piece. So we can measure the magnetic field inside. That is a dependent variable. All right. So independent variable is I, which means I'm controlling H. Okay, because of the free current, and I measure the B between the two pole pieces. And how do I measure? By using a Hall probe. I've described to you the Hall experiment. So similarly, yes, we put a Hall probe and we can measure the magnetic field. But in contrast, in electrostatics, let's say here is a capacitor with a dielectric in between. What we apply is a voltage, and we can apply and measure the voltmeter. Okay, we don't actually give free charge or measure D. We actually measure volt and hence the field, and of course supply the voltage from some source. That's what I meant by this. Okay, so apply voltage. So symmetry often allows H calculation to be easier in presence of magnetic field, because if you want to do B calculation of B, then you have to constantly take care of both free current and the bound current. And bound current sometimes comes as a response to the free current. All right, and hence it's often easier, if symmetry allows it, than calculation of H using the free current and then come back to the magnetic field and the bound currents. We'll see that while solving problems. Okay, so of course, so this becomes an easy way, just like Gauss's law. If symmetry allows it, then Gauss's law is the simplest thing to use. Similarly, if the symmetry allows it, the Ampere's law with free current becomes an easy thing to do. All right. So in absence of symmetry, one must look for some boundary conditions or some other constraint to compute H, if H has to be computed first. Okay. So there are crucial differences between B and H, of course, and that is why we have two different variables. Okay. So, but let's make it explicit. In free space, we know now that del cross B is mu naught J, and divergence B is always 0. All right. But inside the material, okay, it is del cross H is JF, Okay, of course, this is true anywhere, but is more convenient in the material. I should not say in matter, but more convenient because of magnetization. But then divergence of B is zero, but divergence of H is not zero. That's a very crucial difference. And that is why B and H cannot be on the same footing. Okay, because divergence of H now depends on, okay, so if I, divergence of B is always zero, so the first term is zero, so minus divergence of M. Okay, and hence these two cannot be in the same footing. All right, there are many special cases, of course, when divergence of M can be zero, and then they become almost equivalent. Okay, and just simply having a one or the other can give you the other. So in general, therefore, delta divergence of H is not zero. That's a crucial difference. Okay, uh, H is typically zero only when B is parallel to M in uniform material. If it is uniformly magnetized, okay, and B is parallel to M, in that case, divergence typically, I mean, I will not make it a rule, but typically it comes out like that, okay. But one must consider the source of H coming because of a divergence of M is not, okay, non-zero. So is H zero if there is no free current? Obviously not. Okay, because there can be just consider have a bar magnet. Okay, so in fact, I would like you to, as an important task, you should try and sketch both B and H field for a short cylindrical bar magnet. Okay, just because there is no free current, if there is a bar magnet sitting on my table, there is of course no free current. Does that mean H is zero? No. All right, you should actually do that. Take this short cylindrical magnet with a magnetization pointing in the this axis, and now plot both B field and H field. That's an important task. Please do that. Okay. So let's go to boundary conditions for B and H. We have done this quite enough number of times. So this is quite easy for to do. So we know del cross HJF, okay? And we know that divergence of, so these are the two conditions that will give us the boundary condition H, okay? And so let's, this will give you that the parallel, okay, between H and below. I'm not redoing, we have gone through this both in electrostatics and magnetostatics, okay? So H parallel above and below will be Kf, is the free current at the surface cross N. If there is no free current, then of course H parallel is equal to above and below is the same, okay? And the perpendicular one, of course, will depend on the change in magnetization. So this is a simple boundary condition for B and H. Okay. So how does that compare with our uh, magnetic field? Parallel, of course, mu naught K cross M. All right. And B above and B below is equal to zero. That is, okay. And we have obtained this from these arguments, just to remind you. Okay. You can always draw up above and below and take a proper loop and use either the magnetic field, either the in surface or perpendicular to get this boundary condition. But this is quite obvious here. Okay, so in presence of materials, these boundary conditions are sometimes more useful. Of course, these are always true. Okay, but these can be more useful in when we're dealing with magnetic material. Right? It's that's important to keep in mind. Let's take up an example, a very small and compulsory example in some sense. Okay, that is find H for a long circular copper cylinder carrying uniform current I. I mentioned copper. It is not a strictly a very magnetic material. All right. So in some sense, this is a copper cylinder, a long, almost infinite. Okay, and there is a current. There is a current I flowing, let's say. All right. And then I have to find H everywhere. So what do I do? So one can note that copper is a weakly diamagnetic material. How do I know? I am telling you. Okay, but we don't need any information about the bound currents as long as you are assured that if there is any bound current because of the material, then they are along the longitudinal direction. Okay, if that is true, then we can go ahead and use uh, the fact that if the current is axial, then the B and hence magnetization and hence H will be all be circumferential. All right. Okay. So B, M, and H will all be circumferential as long as I'm sure that the current is axial. All right. Then of course I can choose my Amperian loop. Okay. H dot dl is IF enclosed. So I can choose an Amperian loop. So and calculate, let's say S less than R. Okay. And then 2 pi S. H is of course symmetry is make sure that it's same everywhere. So I have free current and enclosed. I have to only consider free current. Okay. I don't have to at this stage in using this worry about the bound currents. So that is of course the fraction of the is uniformly going. The fraction of the current pi s squared divided by pi r squared. That is that, and hence I can calculate uh, for the inside for less than s is equal to r, h is simply I by 2 pi, pi cancels, 2 pi r squared. Of course, it keeps increasing with s and pi. Okay, so it's circumferential, but as I go in s direction, it keeps increasing. All right. So that is my h inside. Okay. What about the calculation of B inside needs knowledge of boundary currents, and H I can do, okay, because it's and in the what are the kind of bound currents I expect here? Will be running anti-parallel to the current inside and parallel to the current on the surface. Okay. However, that effect would be negligible since copper is a weak diamagnetic material. All right. What about outside? Okay. For outside, uh, it's pretty easy to do that. Okay. Then H is simply pi by 2 pi s pi. So for any Amperian current and uh, and hence I can calculate B. B is of course okay mu naught I 2 pi by s pi, right? Because as if it's a one where at the center. So I have calculated through going through H without knowing bound currents. That's what is the illustration is all about. Okay. So a magnetic susceptibility and permeability. Let me define magnetic susceptibility before I come to this table. In magnetic linear media, there is diamagnetic and paramagnetic. Okay. So this is linear media. Magnetization is considered proportional to the applied field. Just like in electrostatics, we had a P is a linear media if the polarization is proportional to electric. Okay, so here instead of electric magnetic field, we take the M, the magnetization is being proportional to H. This is by conventional tradition. That is, so M is H, and hence susceptibility is the proportionality constant. And that is the susceptibility written down for different materials, which are diamagnetic materials and which are paramagnetic materials. I'll come to that. Okay, so chi m is the magnetic susceptibility of the medium. So for magnetic, it's a linear media. Okay, I can write down B is mu naught m plus h, and hence I can, if it is linear, then I can take chi m out. Then I can write down B in terms of h alone, and mu naught 1 plus chi m is the new permeability. All right. So B is equal to mu h, where mu is the mu naught plus 1 plus chi m is the permeability. Okay. Uh, okay. So often one defines relative permeability of a material as relative permeability also. Okay. But chi m. So chi m is just like we had electric susceptibility in case of um, electrostatics, but here is magnetic susceptibility. But remember, magnetization is proportional to H, not B. All right, the way it is defined is chi m. So for a diamagnetic material, the magnetization can be opposite to H, okay, and hence it is negative. These are diamagnetic materials, okay. Whereas in a paramagnetic materials, it's positive, okay. Even oxygen, liquid oxygen also is paramagnetic, okay. It can be attracted by a magnetic field. So it's my bismuth is one of the most diamagnetic materials, okay, which is -1 × 10⁻⁴. Otherwise, the very, very small quantity, all right. So susceptibility, most of these are linear materials. If chi-m is itself a function of H, then we call it nonlinear material. Most of the ferromagnetic materials or frozen in magnetization are that kind of material. Because mu is a magnetic permeability of the medium. Let me give this is sort of a general knowledge. We don't use it very much in this course, but to keep the thing complete, to make it complete, there are three kinds of main magnetic materials: diamagnets, paramagnets, and ferromagnets. I have just given a hint of the kind of origin. So for diamagnetic, of course, relative permeability is less than 1, okay, because chi is negative. And what is important to remember that in diamagnetic materials, magnetization M is opposed to B. Okay. In fact, you can experimentally you can find out whether it's a magnet, it's diamagnet. If you keep it in a non-uniform magnetic field, then this material will get forced to the area where there is less magnetic. Right? We'll understand that better also. Well, superconductors are considered as perfect diamagnet. Then mu r is Earth chi m is -1. Okay, superconductor. We'll come to that maybe in the next chapter. The origin of diamagnetism is in the orbital motion of the electrons. I'll explain that briefly. Okay. The examples we have seen: the bismuth is one, bismuth, copper, germanium, silver, gold. Most of these materials which are non-magnetic are diamagnetic. Okay. Paramagnetic, here it is magnetization is parallel to magnetization induced, and this is also quite weak, but it's positive. This was negative, it is quite positive. And origin is the dipole moment of the spinning electron. Okay, example: aluminum, magnesium, titanium, tungsten. All right. And in ferromagnetic, the relative permeability can be much, much larger than chi-m is much, but this is non-linear material. Okay, so the chi-m could be 100 to a lakh. Okay, 10 to the power 5. But these operate on terms of magnetized domains. You can see the material has already magnetization frozen in domains. And once you apply a magnetic field, when you magnetize, then these domains sort of, by interaction, the complicated mechanism which some of you will study in your higher courses. Okay, and then these domains sort of align themselves and produce a magnetization, a much stronger magnetization, that is B. Okay, so examples, of course, the three most important magnetic materials: cobalt, iron, nickel, and there are many alloys. I've just given an example of mu metal. This is just for your being familiar with at least magnetic materials on a name calling basis. Okay. In nonlinear magnetic materials, in this course, we are not teaching nonlinear magnetic materials. Okay. But just to make it complete, I would like to just mention that ferromagnets require no external fields to sustain magnet. They are already, okay. The alignment of the magnetic field is frozen in. If you look at a ferromagnet, then it will look like the spins are all aligned. Okay. Or they're actually in domains. This is a picture of a domain in which this can be actually pictured with this, with the magnetization is pointing in this domain. All right. So, and one of the signature of ferromagnets is the fact that there is hysteresis. It remembers history of its material. What has happened to it? Okay. In linear materials, you take off the magnetic field, it forgets what happened to the magnetization. Magnetization goes away. But here, there is a magnetization history is remembered. okay, and that is expressed in terms of M, okay, and a current for a paramagnet, or more popularly, it is B, okay, and as I told you, H is the independent quantity because the free current that I'm using in a solenoid, for example, Ni, so that is H, and the B that is measured, okay, or magnetization is measured, okay, and then it is uh, first thing, it is non-linear, okay. If it is linear material, then M and H must be linear, but it's non-linear, and it changes with respect to field H, and it saturates, and there is a coercive field, okay, for it to get completely demagnetized and then magnetized in the reverse direction, and so on. But this you will study in some other course. I'm just giving it to you for at the moment for general knowledge. Okay, and of course it comes from unpaired electrons and is alignment between domains that controls ferromagnets. It's a hugely complicated mechanism. I hope if you are doing physics or in electrical engineering, you are going to do about magnetic materials, you'll have to learn this a lot more. There is nonlinear magnetic materials, just as an extension of that. The ferromagnetic order is sort of every magnetization is lined up. Let's say these are spins, and all spins are lined up. That's called ferromagnetic order. But in some materials, there is order, but there are alternate. Okay, these interactions are minimum energy configuration. Okay, and depending upon the nature of interaction between spin and spin, many such orders happen, and this is called antiferromagnetic. There is no net that's so nicely ordered, but the neighboring spin, okay, cancels out the neighborhood, and hence the total magnetization can be zero, but there can be a very nice order. These are antiferromagnetic order. And of course, it gets destroyed at some temperature. The temperature dependence will not go into that. But since many of us will be doing electrical engineering later, at least once would have heard the ferrimagnetic order. In this, what happens is that this is doesn't perfectly cancel in one direction. The other direction is smaller, is ordered, but the spins, the opposite spins are in opposite directions in order, alternate, but the magnitude doesn't match. So there is a net magnetization. Okay, and these a important class of this this is called ferrimagnetic order. An important class of subclass of this material are called ferrites, and it's extremely important for as an engineering material. Uh, and these are crystals. There's actually spinel crystallization containing oxides of magnetic elements. They are ceramic-like materials. What is important is they are magnetic material but with low conductivity. Okay, so and because the low conductivity and magnetization permeability is high, less losses due to eddy current in high frequency applications, microwave applications, transformers where there is AC current. Okay, the eddy currents and the losses are less, and hence they are very important in many applications. They're used in microwave applications, as in course of the FM antennas, transformers, and phase shifters. You're going to learn about that. Even magnetic disk memory devices in computers, okay, use a hugely important material called the yttrium iron garnet or YIG. This is just for your general knowledge. All right. So let's take it some examples. Uh, take a long solenoid, let's say n turns per unit length, small n, okay, and current I, and as a field code of linear material of susceptibility chi m. Find the magnetic field inside the solenoid. This is a typical uses of magnetic material. That is, you have a solenoid and you have put a magnetic material inside, and you want to find out the magnetic field. Okay, so so this is the solenoid, and you have filled it with a core, and there's a current I going circumferential. Okay, and of course the current is in phi direction, and the chi m is the magnetic material. It's simple. Okay, but so the free current route is important here, since you do not know the bound currents. All right, so we can take advantage of the symmetry. It's a long solenoid. Okay, and hence we can get back to our the Ampere's law for free current. All right, and hence I can write down in this case it's simply NIK. Okay, so the current is phi, and hence by all the symmetry rules that we have learned while calculating B for a solenoid, exactly same symmetry arguments will be here, but it is H. H is simply Ni, Ni is the surface current K. Okay, so it's K phi, and hence the H is uh, in this K direction. All right. Um, so for inside, that is for S less than R, we can always write down B is equal to mu naught chi m. Since I know H, I can write down mu into H. Okay. And now I know B. Okay. So assuming the medium is paramagnetic, that would be slightly enhanced because chi m is positive. If it is diamagnetic, then chi-m is negative, so it will be slightly reduced. Okay. The bound surface current can be you can compute now also what is surface current because we know m cross n is chi-m h cross n, so chi-m n I phi. So there is a bound surface current which is phi, and it will depend upon what is chi-m. Okay. If chi-m is negative, then the bound current will be opposite to the free current. Okay, and if that is if it is diamagnetic, if chi-m is positive, which is this paramagnetic, then bound current adds to the same direction as the free current. All right, so that's what I'm writing it down. If chi-m is the bound is in the same direction as the I, and if chi-m is less than, it is in the opposite direction. Okay, this is a typical use of the magnet H that we have learned. First find out H, then you can find out B, and from the B you can find out the bound currents. The typical use. Now let's take an example of instead of this is a very widely used configuration of a toroidal, okay, and filled with a core material, and there is a small air gap here, A, okay. There's the area A, but suppose I have a small air gap here, all right, so of length L. So I open up a air gap of length L, okay, has a filled core of permeability mu, and the circular radius is much, much less than R, and the core has a narrow gap of length, okay, L. So find BH inside the core and H in the air gap, suppose. So the free current route is again important here, since you do not know the bound current. Okay, I repeat that again. So from there is a nice symmetry here, and hence I can use the symmetry. So H dot dl is of course n is the turns, total number of turns, total current, and hence if I this is the Amperian loop, then the total enclosed current is n into I. Okay, so in terms of I first let me have H. Then let B and the C will be in the core. Okay. If suppose I have a air gap here, then that will be BA in the air gap. Okay. So then of course I know the normal is will be equal. So the magnetic field in the core will be magnetic field in the air in this configuration. Okay. And that is nothing but and the magnetic field is of course is in the phi direction here. Okay. The current is going like that. The current is going like that, and the magnetic field is turning around this in the phi direction. Okay. So this is BC and this is BA in the air gap. So I can always write down my XC as BC by mu. Permeability is given and phi. Okay, that's the core. It's meaning it's in the core. Okay. And of course, HA is instead of mu is mu naught. So this is BA by phi. Okay. So now I can plug in this H into this equation. All right. So using now I'll using the Ampere's law. It is simple. Okay. So this is 2 pi. There is a air gap L. Then BC by mu 2 pi R minus L, and BA by mu into L, and that must be equal to just rewriting this with this symmetry. All right. And after that, it is simple algebra to find out is that the B of in the core is mu naught 2 pi RL plus mu L. So this involves both mu and mu naught, and Ni is of course the total current, and B in the core is in the phi direction. What about H? H would be simply, if I know B, I can find out H. It will be simply divided by mu. So mu naught, same Ni phi. So in the core, I know B and H. All right. What about the air gap? So air gap, because, okay, so that would be mu by mu naught. Okay, so that's obvious. Okay, so, and hence you can see that to compare this and this. Okay, the H in the gap is stronger, is mu naught and is mu. All these are same. So H in, if there's the air gap here, then H in the air gap is stronger by the relative permittivity. This mu is given, but mu by mu naught. Suppose I put a ferromagnetic material of something like a 500 or so, then the in the air gap, the H is 500 times stronger, okay, than in the core. And that's why such configurations are used in a magnetic, as a toroidal magnets. Okay, so let me take up another bus boundary value problem at the last example. At the interface between one linear magnetic material and another, the magnetic field lines bend. Okay, show that, and how do they bend? I'll show that, I'll draw the diagram. So assume there is no free current at the interface, and this is B1, and this is theta 1, and this is B2, is theta 2. It's a simple application of the boundary condition that we have learned, and exactly similar thing we have done it for D1 and D2, okay, in electrostatics. So let me go through it. So at the interface, of course, the perpendicular component of B is continuous, okay, and the parallel component of H is continuous. That's the heart of the problem. Okay, the perpendicular component of B is continuous, and the parallel component H is continuous, and hence I can write down B1 perpendicular to B2 perpendicular, and H1 parallel is equal to H2 parallel at the interface. But I know this. B is mu H, and hence I can now use that to write down this, and this will give me B1 parallel by mu1, okay, and B2 parallel by mu2 from here. And then I can find out tan theta 1, B1 parallel by B1 perpendicular by the geometry itself. Similarly, tan theta 2 is B2 perpendicular parallel by B2 perpendicular. Okay, and then I take the ratio tan theta 1, tan theta 2 by tan theta 1, B2, B1 perpendicular by B1 parallel, B2 parallel. So this cancels because these two are equal, and hence we are left with B2 parallel by B1 parallel, which is nothing but mu2 by mu1, and that is what is proved. Okay, you can compare this with the electrostatic case that we had done earlier. All right. So with that, I sort of come to the end of the magnetic materials. In the practice problem and in the home assignment, I'll give you some actual cases like how the magnetic interaction and a feel for the actual magnets that's available in the market. But we'll do that as a part of the practice problem and home assignment. Thank you.